Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we are going to apply the definitions of marginal density function and conditional density function. Okay? So, the application will be solving a problem from our textbook. Okay, here's a problem I would like to work on with you. So it's exercise 5.27 from our textbook. Okay, so as you can see, part A is about marginal density functions. In part B, we have to find a probability, a conditional probability, right? But parts C and D are about finding conditional density functions, okay? And then part E is about, again, finding a conditional probability, okay? Okay, so we are going to be doing all of them. Okay, first let us start with the marginal density functions for y1 and y2. Okay, let me change notations here. Okay, instead of y1 I'm going to be using x, instead of using y2 I'm going to be using y. Okay, so here we go. Exercise 5.27. Okay, so again, first let me change labels, if you will. Instead of using y1 I'll use x, instead of using y2 I'll use y. Okay, so let me rewrite that density function that we have there, that joint probability density function. Okay, so it's going to be 6 times 1 minus y2, so I'm going to have 6 times 1 minus y. Okay, and that holds for values satisfying an inequality, right? y1 must be less than or equal to y2, y2 must be less than or equal to 1, and y1 must be greater or equal to 0. Okay, so y1 is less than or equal to y2, meaning x, right, using my new labels, x, y, and 1. Okay, and we know that if the joint PDF is 0 otherwise. Okay, part A, as we said, it's about finding the marginal density functions. Okay, so how about we find the marginal for x and y. Okay, find marginal density functions for x and y. Okay, okay, well, it should be, yeah, okay. Here we go. So first, as you can imagine, what we want to do here is apply the definition. Okay, let me remind you, I believe that definition is here, page 39. Yeah, so if you want the marginal density function of the random variable y1, right, what you have to do is integrate the joint with respect to the other variable y2. On the other hand, if what you want is the marginal density function of y2, right, what you have to do is integrate the joint density function with respect to y1. Okay, so that's exactly what we're going to be doing. Okay, okay, so let me remind you, by definition what we have is we want, let's do x first. Lowercase f, that's the one I want. The marginal of x, okay, is going to be just integral from negative infinity to infinity of the joint density function. And since we want the marginal for x, we have to take the integral with respect to y. Okay. Okay. So now let's see. So we know that outside this region, okay, we have nothing, right? 0. Okay. So the only part that counts for y is the y's that satisfy these inequalities. If y is less than or equal to 1, and if y is greater or equal to x. Okay? So what we have here is this. This is going to be integral from x to 1 of our joint PDF with respect to y. Make sense? And again, we can see those restrictions here. Okay? Clearly y must be greater or equal to x, and y must be less than or equal to 1. Okay? Now let's try and do that integral. We know that we can factor out that 6, right, by the linearity of integrals. So let me pull that one out. Here it goes. Okay, now note that this is the same as 1 minus y to the power 1. Okay? If we had a negative 1 outside, right, clearly the derivative of 1 minus y squared divided by 2 would give you this. Make sense? If we had a negative 1 here, the derivative of 1 minus y squared divided by 2 would be this. Okay? So we need a negative 1 here. So we are multiplying by just a 1, so we can easily find this integral. And I'm going to say something about this in just a sec. So what we said we have here is this guy, 1 minus y squared divided by 2, right? Clearly, if you take the derivative of this guy, 1 minus y squared divided by 2, you end up with this by the chain rule. 2 divided by 2, those cancel out, 1 minus y to the power 1 times -1. Okay, so that's one way. And we have to evaluate at x and at 1. Okay, now another way of doing this is, instead of doing what we did, just break down before, instead of having this, just had that. So we could do two integrals, right? The integral of 1 with respect to y minus the integral of y with respect to y. Two choices, okay? But they are both valid choices, okay? Anyway, so if we're careful, we end up with the same result. Okay, so when we evaluate at 1, 1 minus 1, 0, right? So the only one that is going to count is when we evaluate at x. So what we end up with here is minus, because we have a minus, right? We have evaluation at 1 minus evaluation at x. So minus times minus, we're going to have a plus, and we have x here, right? So in the end, what we have here is 3 times 1 minus x squared. Okay? So that happens to be our marginal with respect to, well, the marginal for x, right? Okay, now we need the support, we call it, the values for the x, right? So note that x must satisfy something here. X must live between 0 and 1, okay? Between 0 and 1. Agreed? Yeah? Okay. So, it's always a good idea, if possible, to check that you have a legit probability density function. Now, note that in this case, we can quickly and easily argue that this expression here is in fact a legit PDF. So, let me just say something. Note that, and when I'm done doing this, you'll see exactly where I'm going, what I'm trying to say. Note that x to the 0 power is the same as 1, right? So if I had x to the 1 minus 1, 1 minus x squared is the same as 3 minus 1, right? Interesting. So it seems that this guy could be a beta with parameters alpha equals 1 and beta equals 3. So if that was the case, that 3 would need to be, remember that a beta distribution is the gamma function evaluated at alpha plus beta, meaning 1 plus 3, 4, divided by gamma evaluated at alpha, 1, and gamma function evaluated at beta. We know that gamma at 4 is the same as 3 factorial. 1 factorial is just, you know, I mean, gamma at 1 is the same as 0 factorial. 0 factorial is 1. And gamma, the gamma function evaluated at 3, is the same as 2 factorial. But 3 factorial is the same as 3 times 2 factorial. So the only one that is going to survive is that 3, right? So these two guys cancel out. Those that 2 factorial with that 2 factorial, so we only end up with that 3. Okay, so bottom line, what I wanted you to see is that in this case we were able to very quickly realize that this expression is a beta distribution, right? And that's a legit probability density function, and it has the right support because beta distributions live between 0 and 1. Okay? Okay. Now let's do the other one. Let's try and find the other marginal, the marginal of y. So let me borrow this, and then I'm going to be careful, right? We have to make some changes. So now let's do y. So again, just by definition, we know that now if you want the marginal for y, you are going to integrate the joint PDF but with respect to x. Okay, now let's take a look at the original joint probability density function. So since now instead of integrating with respect to y, we are integrating with respect to x, note that x has these two restrictions. X must be greater or equal to 0 and less than or equal to y. Okay, x must live here, okay, between 0 and y. So let's do that. Zero and y, right? Okay, and that's the joint probability density function. Okay, now note something really nice about this. 6 times 1 minus y with respect to x is just a constant, so we get to pull all that out. So let's do that. That will be our next step. Oops. And this will be just a 1, right? And that's an easy integral. That's just going to be x, right? Agreed? So we have this. And we have x, and we are going to be evaluating x at 0 and y, right? Okay. So in the end, what we have is 6 times 1 minus y times y, because 0, you know, when we have 0, well, everything disappears. So let me write it down like this. Okay, that's what we have. And we also have, right, that y must live between 0 and 1 for any x. Okay? Okay. Make sense? Now, again, note that we could argue that this guy is also a beta distribution. Note that y to the power 1 is the same as y to the power 2 minus 1. 1 minus y to the power 1 is the same as 1 minus y to the power 2 minus 1. Okay? So it seems that this guy is a beta with parameters alpha equals 2 and beta equals 2. And we have the right support. We know that the non-zero part of a beta distribution must be the 0-1 interval. Okay? So again, it seems that we ended up with a legit probability density function. And these guys, marginal density functions, are supposed to be just, you know, legit probability density functions. Let me just say that it seems that marginal of y is a beta with parameters alpha equals 2 and beta equals 2. That's nice, right? Okay. Okay. So we are done with part A. We found the marginal density functions. Okay. The other part that we wanted was finding a probability. I think it's okay. Let me just look for that slide with our problem. Okay, found it. So slide 69 has you know, our problem. So part B is finding this probability, the probability that y2 is less than or equal to 1/2 given that y1 is less than or equal to 3/4. Okay, so let's write that down. Okay, but remember that I changed notation, so I will have to translate the problem to my new labels. So what I want is the probability that y2, meaning y, is less than or equal to 1/2 given that x is x is less than or equal to 3/4. X less than or equal to 3/4. Excellent. Okay. So first, let's remember what the definition of conditional probability tells us, right? So what we know is that the probability of A given B is the probability of A and B divided by the probability of B, right? So something similar here. So we want the probability of this happening and we want this to happen too. And then we divide by probability of this happening, right? Make sense? Just the definition of conditional probability. A given B equals probability of A and B divided by probability of B, right? Okay. Now let's translate this in terms of joint, in terms of something that we can do with our joint probability density function, and maybe in terms of marginal. Now we have marginal density functions as well. So for the top part, we need the joint, right? Because we have both of them. Okay. Now let me place these guys in order. First the x, then that y. Okay, that looks better. So the top part, the numerator, we can find using a double integral because it has to do with the joint. Okay, so let's write that down. Another integral. Okay, so what we want is joint density function is, oh no, not that one, right? That's the marginal. This is the joint density function. Okay. And note, by the way, I'm going to write that down in just a sec. Oh, well, I might as well tell you. So note first, before I write that down, that integral, this one, the numerator is equivalent to this for the joint. Okay, make sense? Okay, so now if we are going to be integrating with respect to x first, right, then x must be less than or equal to 3/4. But what we know about x is that, well, you know, that guy must be below y, right? X must be below y. From 0 to y, and x and y, that one goes from 0 to 1/2. Okay? Make sense? Now let's see this one here. That one is just the marginal, so that one is just going to be this guy and we want to integrate that guy from 0 to 3/4. And this one, it's going to be just from respect to x. Make sense? Can you see that? Yeah? Okay. So, first one, right, is not going to be hard. We just, you know, factor this one out. that's constant with respect to x, right? Now the integral of 1 with respect to x is just x. We're going to be evaluating from y to 0, so we end up only with a y, right? Let me just say that. And then we have the y, okay. And then we have this guy here, okay? So we can easily find these, right? It would be just 6y times 1, well, 6y, right? It would be the integral of 6 times y with respect to y. Then we would have minus 6 times the integral of y squared. That's easy to find. We could do something similar here, right? We could easily find them using calc. Let me do this quickly using R, okay? And then I also get to remind you how you can find those integrals easily using R. So for the first one, for the function in the numerator, let me define a function f. It's going to be a function of y, and what I want is 6 times y times 1 minus y, okay? And then I want to integrate the function f. The lower limit is going to be 0, the upper limit is going to be 0.5 or 1/2, 1/2. There, so it's 0.5. That's our numerator. And again, it's easy to do that integral using calc, right? It is not that bad, but you know, we have access to R. We might as well do this quickly using R. So function. Now this one is going to be a function of x, and it's defined as 3 times 1 minus x squared. Okay? Okay. So now what we want to do is integrate that function g. The lower limit is 0. The upper limit is 3/4. Okay? So that happens to be 0.984374, right? Now, I think that if you do that by hand, you end up with this, which is exactly the same. Okay? Okay. So now what we have here is 0.5 divided by this, and that's just roughly this number here. Make sense? Okay. So that's that probability. That's the one that we wanted from part B. Let's do one more. Let's do part C. We want now the conditional. Okay? Before we move on, note that what I did here is that in the numerator of the previous probability that we wanted to find, well, first I integrated with respect to x and then with respect to y. You could have done it the other way around. Okay? And try and do that. if you're careful and if you integrate with respect to y and then with respect to x, you should end up with the same answer. Okay, that's a theorem from calc. I believe that's Fubini's theorem. Okay, anyway, let's keep going. So part C. So what we want for part C is the conditional, right, density function of y1 given y2 at a particular value. Okay, so now I believe that the I believe that definition is there. Yeah. So anyway, it's simple. The definition of a conditional density is just the joint. If you want the conditional of x given y, is just the joint divided by the marginal of y. If you want the other conditional, y given x, joint divided by marginal of x. So as you can see, this is just a generalization of a condition of the formula for conditional probability. Probability of A and B divided by probability of B, if you want the probability of A given B, right? And if you change, instead of the probability of A given B, if you want the probability of B given A, then you divide by the probability of A. So same thing here. See? Same correspondence. It's just an extension. Okay. So we want that conditional probability. Let's find it. So that conditional density, sorry. So by definition, what we want here is, let me do first the conditional of x given y. Okay, so by definition we know it's just joint divided by the right marginal. The joint is this, and the marginal that I need is the marginal of the random variable y. Okay, there we are. So joint is this guy. Marginal. Our marginal of y is this. Now note that this is going to be very easy in this case. Those 6's just cancel out. The other term, 1 minus y, those guys also cancel out. So what we end up with is 1 over y. Okay? And now note something interesting here. That y must satisfy some conditions, right? We know that we have these conditions to be satisfied. Okay? Now, in this case, if we want to be very, very careful, right, what we need is that y to be greater, right? We want that well, that y must be greater than 0, right? But I mean, in a sense, it must be like that, because if we don't have that, right, if y is not greater than 0, this collapses into a point. anyway, just saying, remember that we can't divide by 0. But now, here goes another comment. You have 1 over y. Note that this is a conditional probability density, right? So for instance, if y is 1, 1 over 1 is just 1, and then you would have an expression that looks like this: 1 if x lives between 0 and 1. Okay, if you had that, you go, oh, that's a uniform in 0, 1, right? So what we have seen here is, oh, it's a uniform distribution. If y is, for instance, 1/2, right? F of x, given that y is 1/2, you would have 1 over 1/2, it would be 2, right? And this guy would be, 0. Well, it would be 2 for x's that live between 0 and 1/2. And then, oh, it's a uniform in 0 to 1/2. Another uniform, right? So, anyway, so as you can see, it's a uniform that is conditional on the value of y. That's why this guy is a conditional probability density function. Okay, so it's a uniform. Which one? Oh, you tell me y, and you tell me the y, the value of y, and then I'll tell you which uniform you're dealing with. Make sense? Okay. So now let's do the same for the other one. The other conditional density will look like this. F of y given x is just going to be the same joined divided by marginal, but in this case the marginal is the marginal of x, right? So let me borrow the joint from what we had before. That one is not going to change. The one that is going to change is the bottom part, the denominator. This one is not going to be the same, right? Let me go get the marginal of x. Where do we have it? Here. Beautiful. So now I want to divide by this guy, just the bottom part. Okay, there we are. And again, we have some restrictions. Remember those restrictions? Same restrictions that we had here. Okay. So in that case, it's not so easy to check, right, that this guy is a legit probability density function. But what you have to see is also that this interval here depends on x, right? So for instance, if x equals 1/2, right? So you have that y goes from the interval, well, lives in the interval 1/2 to 1, right? And this is going to change accordingly, right? Make sense? Yeah? Okay. So, next, let's do the next part, because we're done with parts C and D. Let's do part E. Okay? So, there, the only thing that we want, note that in this case, we have this. The probability that y2 is greater or equal to 3/4 given that y1 is equal to a particular value. So we know that in the case of a continuous random variable, the probability of assuming exactly one value would be 0. But basically what they are asking us here to do is just computing the conditional density function of y2 given y1 at that particular value, 1/2. Make sense? Okay, so let's do that. So let me just translate to our labels. So in that case, what we have is the probability that y is greater or equal to 3/4 given that x, right, the random variable x equals 1/2, right? So that's a given. Okay, so basically what we want is the probability that y, we know that y must be between 0 and 1, right? But we want that to be greater than 3/4 and up to 1, right? And the one that we have to use here is the conditional probability of y given x, right? X equals 1/2, right? And then this is with respect to y. Okay, oops, better. Okay, now let's compute this quickly. From 3/4 to 1, and then the one we want is this guy evaluated at x equals 1/2. 1 minus 1/2, 1/2 squared is 1/4, right? So what we're going to have here is first, we can simplify this, right? This is just 3, and 1 minus 1/2, oh sorry, this is 2, 6 divided by 3, 2, right? So 1 minus 1/2, 1/2 squared, 1/4, and then it's times 2, so what we're going to have here is just an 8. Makes sense? And we don't need this anymore. So make sense? I just evaluated at x equals 1/2. Again, 6/3, that's 2. 2 times 1 minus y divided by 1 minus x squared, but when x equals 1/2, this is just 1 minus 1/2 square. 1/2 squared is 1/4, so it's going to be 2 times 4, 8. Okay? Okay. And now, again, this is a simple integral. We could break it down into two simple integrals. The integral from 3/4 to 1 of 8 dy minus the integral from 3/4 to 1 of y dy. That's easy to do, but let me do it using r, and then you can check using calc that we end up with the right answer. Okay? Okay, so let me define a new function h, a function of y, 8 times 1 minus y. Okay, then we want to integrate h, lower limit 3/4, upper limit just 1, so that's just 1/4. and we are done. Make sense? Okay, so let's summarize what we did here in this video. In this video, what we did is we applied a couple of important definitions, and we used them also to find a few probabilities. Okay, we talked about the definition of conditional densities, right? And we know that it's just an extension of the concept of a conditional probability. And we also talked about the concept of marginal probability density functions. Okay? Make sense? Well, that's it for now. Thank you so much for watching. Please keep working hard and take care. See you next time. Bye.